You're welcome to another broadcast of Science Spectrum with Don. This class in fluids and hydrostatics, or just say hydrostatic fluid, is actually a class that's tailored to the request of some of my online audience. So I'll do a job that'll be somewhat interesting, fluids and hydrostatics. So let me start off with this concept of pressure. Alright, the first key question you may want to ask is, what is pressure? We often witness pressure in our day-to-day activity. Take for instance, if I exert a force over a given area of this bird that my tongue, comes in contact with, that's pressure. So when you press on the knob of a button, you're actually exerting a pressure over a given area that you exert the force on. So if we define pressure, which I denote with a symbol P, it's really the perpendicular component of a force you apply or exert, of an applied force. So I will denote the perpendicular component of the applied or exerted force by F with a subscript of this symbol, so it's at 90 degrees with the surface, over the area A of a body or an object. So if I were to represent this mathematically, this relation, pressure is really the perpendicular component of a force over a given area on which the force is either applied or exerted. Force is expressed in SI units in Newton, and area officially also in SI is in square meter. So, but no one would, for now, represent the unit of pressure officially as Newton per square meter, but rather it is said to be in Pascal. So Pascal is actually a French mathematician who contributed a whole lot to this concept of fluids and hydrostatic, particularly pressure. All right, so let's move on. Now, from this relationship you see here, if I give you any two quantities, there are three quantities here. You have the pressure for one, you have the perpendicular component of the force you apply, then you have the given area. If I give you any two values of these quantities, take for instance, I tell you what the pressure and the area is, you could tell me what the force is. If I tell you what the force and the area are, you could tell me what the pressure is. So if I give you any two values of these quantities, you could really tell what the third one is. So that's just the relation between these quantities you see here. Now, if you look at this equation, you would find out that pressure is proportional to the force, the applied force. What it implies is, if you increase the force, consequently, the pressure also goes up. What it would also imply is that if you decrease the force, consequently also the pressure drops. But when you look at the relation between the pressure and the area, it turns out to be that the pressure has an inverse relation with the area. So what it implies is an increase in the surface area of a body would result to a decrease in the pressure. And while a decrease in the surface area of a body in which you exert a force would imply an increase in the pressure. So that's just the mathematical relation between these three quantities. Now you may need to beam this for a while I clean this up and proceed with the class. Alright. Now, let me stick in some numbers, okay, so we could have a feel of this relation. So let's take, for instance, this is a given, it's a given. So let's say I tell you what the force is. Let's take for instance, let's say you exert a force of 50 Newton. This is the force, 50 Newton, and let's assume it's a perpendicular component of the force. And then let's say the given area, you could think of it this way. Let's say you have a balloon like so. So this is a balloon like so. So this is a balloon. So I exert a force with from my hand, but my thumb makes contact with the surface of this balloon. So let's say the area of my hand that makes contact with this balloon when I exert a force of 15 Newton on this balloon, let's say it's about 2.5 times 10 raised to power. Okay, let's say it's roughly 10 raised to power minus 4 square meter. And let's say I take a pin, a needle, and I exert the same force, but the pin would make a smaller contact with the area of the balloon. So it will make a small area of contact with the balloon. So let's say the area, okay, of the needle that makes contact with the balloon under the influence of the same force, because I'm also exerting, but with the pin now, or a needle. So let's say this is about, let me make it smaller, 2.5 times 10 raised to the power minus 7 square meter. So the key question now is, what is the pressure exerted, okay, by my finger? This is my finger. Let me use the precise word, finger. So what's the pressure that my finger would exert on this balloon? That is for one. And for another, what is the pressure by which the needle exerts a force on that same balloon? The force is a given, 15 Newton. So let's go ahead and see. You would really find out that at the end of the day, once I'm done crunching these numbers, you figure out that this relation holds true for a given force. Alright, so let's see this. So to start off with, the pressure from my finger on the balloon, from my finger on the balloon, is the force, the perpendicular component of the force. I just assume it's perpendicular since there is no angle relative to the vertical axis. So per unit area, and the area now has to be the area of my finger. Now you have to take note of this. If the area hadn't been given in square meter, you'd have to convert it to SI units. The same goes with the force. Alright, so the force is 15 Newton, and the area of my finger given, which is quite bigger than this, if you compare the powers of 10, is 10 raised to power minus 4 square meter. And of course, this boils down to, is the same as 50 over 1 times 1 over 10 raised to power minus 4 Newton per square meter. But let me just call this for my convenience. Let me call this Pascal. Pascal. So clearly, this term you see here, 1 over 10 raised to power minus 4 would boil down to be 10 raised to power 4. So I'm left with a 50 over 1 here. So this becomes 50 times 10 to power 4 Pascal. So this is the pressure that my finger exerts on that balloon for this area that my finger makes contact with the balloon. Now this is the A part of the question. So let me call this A, and let me call this B. So I'm done with the A part of the question. Now we move on to the B part of the question. So the pressure the needle exerts on the balloon is really the same force I exert with my hand. That's 15 Newton from this formula. But now the needle makes a smaller area compared to my finger on the balloon. So which is 2.5 times 10 raised to the power minus 7 square meter. So I could make this a whole number. This becomes 50 over 25. Then you have, I'm moving decimal point one place forward. This becomes 25 times 10 to the power minus 1. But I'm adding the minus 1 to minus 7. Right? Let me do it this way. Times 10 to the power minus 1. Then this term is the same as 2.5. I'm making this decimal number a whole number this way. So I have to move the decimal point a step ahead. So you have this term. Then I have times 10 raised to the power minus 7. And of course, my unit boils down to the Newton per square meter. And let me just call this Pascal. So clearly, I could use the law of indices to crunch this. So the bases are the same, the powers are different, and there is an operation of times in between. So I'll add up the powers. So minus 1 plus minus 7, everything boils down to be minus 1 minus 7. And that turns out to be minus 8. So I have 50 over 25 times 1 over 10 raised to the power minus 8. So clearly, 25 in 25 is a 1, 25 in 50 is a 2. So this boils down to be 2 times, now 1 over means I was taking the minus in the power, but I have a minus to start with. So minus times minus turns down to be plus. So this is times 10 raised to the power 8 Pascal. Now, this is the pressure from the needle on the balloon. Now, if you compare these two terms, you figure out that this is way more than this. Why? Because I give it a smaller area. The needle has a smaller area at which it makes contact with the balloon compared to my finger. So you may need to build this for a while I go ahead with the next example. Alright, so the next example is really to make you see why I have to introduce the word the perpendicular component of the force. That's what defines pressure per unit area. Alright, so I give you a given also. You have a given. So the given is, let's take for instance that I have a book, like so, and this book rests on a table. So this is a book, and this is a table. So let's say I give the book a mass of half a kilogram. The book is half a kilogram. And let's say I exert a force on this book, and let's say the force is 16 Newton. But I'm exerting the force now at an angle theta relative to the vertical axis, right? Okay, and so the key question is this: what is the pressure from my hand to the book? That's number one. And number two is, what is the pressure that from the book on the table? These are two key questions I would like to address. Okay? So to start with, let me decompose this force, both on the horizontal and on the vertical component. In other words, if you are looking at the shadow of this force of 16 Newton that is inclined at an angle theta with the vertical, then you would see the shadow both on the x and on the y-axis. So we call those the components of the force. So if I draw a sketch of this now, this is the force F, which is 16 Newton. And of course I draw the normal, this line, the dashed line, the vertical axis, theta. So if I would decompose this force, you could view the shadow of this force along the x direction, like so. So this is really the x component of the force. And of course, in the same vein, you could also decompose this force on the vertical axis, which is f sub y. So if you look at this is 90 degrees. You actually see a right angle triangle here. So if I take the given with this unknown side, if you take, okay, this is really the side the acute angle faces in the right angle triangle. This is the opposite side. This is the adjacent side, and of course this is the hypotenuse side for my convenience. So if you take the ratio of the opposite side, which is the x component of the force, to the given force, which is 16 Newton, you find out that that is it boils down to be the sine. So let me introduce the word SOHCAHTOA, which you may have heard before. SOHCAHTOA. S is for sine. So the sine of the angle of the acute angle of a given right angle triangle is really the ratio of the opposite side to the hypotenuse side. So I may need to clean up this part now. Be here for a while. Alright, so I could move on now. So the x component of this force is really, is really the force. So I'm taking these two sides, f sub x over f, that is the opposite side of the hypotenuse side of a given right angle triangle. That is sine. So this is really the sine of this acute given angle. So if I would cross multiply, f sub x times 1 boils down to be f sub x, this is equals to f sine theta. And consequently, if you do the same, you figure out that the y component of the force is the force times the cosine of theta. So if I would now define the pressure exerted by my hand on the book, is really the perpendicular component of the force, which is really this, divided by the area. So let me take the area of the book. Let me take for one. Let's say the area of my hand that is in contact with the book when I exert a force. This is the area that makes. So let's say the area of my hand, let's say is roughly 0.06 square meter. And so that's the area of my hand now. Okay, so let me start off with this. So the perpendicular component of the force is really F cosine theta over A. The force itself is 16 Newton times the cosine. And let this angle theta, let me say it's 40 degrees for my convenience. So times the cosine of 40 degrees, and I divide it by the area by which my hand makes contact with the book, and that's 0.06 square meter. Okay? So I need to continue from here, from the subsequent broadcast. Thank you, as you stay tuned.